In this video, we're going to look at the qualitative relationships between impulse or change in momentum, the changes in velocity, force, time of impact, and acceleration for different types of collisions. In our first scenario, we have two carts that are exploding away from one another due to the spring force. Cart B has twice the mass of cart A. So I'm going to go ahead and make a little sketch, my excellent artistic skills here, of cart B and cart A. We'll call this one A and we'll call this one B. And we know that they are moving away from one another. I'm also going to identify the positive direction as being towards the right so that we can make some considerations. As we start to consider the relationships between these objects, I'm going to start off by identifying the mass of the two different objects in relation to one another. Mass of A we're going to call just m, and mass of B we're going to call 2m. So we know that there's going to be some mass components in what we need to think about. The first thing we want to look at is the impulse on object A. So that's the change in momentum. We know that whenever there is a collision, the sum of the initial momentums has to equal the sum of the final momentums. That's the law of conservation of momentum, which tells us that these two have to have the same impulse. If they have the same impulse, we know that impulse can be identified by two different equations. One of them is net force times the change in time, and the other one is the mass times the change in velocity. In both cases, impulse is the same thing as the change in momentum, so impulse and change in momentum both have to be equal. The next thing we come to is the change in velocity of the objects. In this case, let's use this equation here. We know that the mass of object A is lower than the mass of object B. Because the mass here is lower, that means the change in velocity has to be greater in order to keep the same momentum. So the change in velocity of A has to be greater than the change in velocity of B. The next thing we want to look at is the force. We know that these two objects are colliding with one another or are interacting with one another in some way. So this is an example of where Newton's third law must apply. Newton's third law says that for every action you have an equal and opposite reaction, or for every force from one object to another you have an equal and opposite force from that object onto the first, which means that our forces do have to be the same. Now we can make a connection between our impulse and our forces using our net force times change in time equation. The two components or the two objects touched each other for the same amount of time. Another way to think about this is if the impulse is the same and the net force is the same, well then the change in time also has to be the same. The last thing that we want to think about here works for the acceleration. We know that according to the second law, net force is equal to mass times acceleration. So if object A has a smaller mass, it must have a greater acceleration in order to maintain the same net force. The next thing we want to look at here is to sketch ourselves a force versus time graph. If we consider both of these components, where let's say the collision happens from here to here because we know that that's the same amount of time, one of the objects is going to have a positive force. That's going to be the one that was moving toward the right, which is object B. And then the other object is going to have the same amount of force over the same amount of time, but now it's going to be in the opposite direction, so it's negative. That's object A. Notice that the area under the curve for B and then the area under the curve for A are equivalent. The force times the change in time. Up next, we have a different scenario. Now we have two eggs of equal masses, that's going to be important, are dropped from a height of 1 meter, so same height. One of the eggs is dropped onto a tile floor, the other egg is dropped onto a pillow. So to sketch this, I'm going to have my two little eggs. We know that they are dropping towards the ground. One of them is going to be dropping onto the hard surface of a tile. The other one is going to be dropping onto a pillow. We're going to consider the same types of equations. In this case, the mass of A is going to be equal to m, and the mass of B is also equal to the same mass. As we consider the impulse on the two objects, the relationships that we're looking for now are pretty much between the egg and the floor or the surface that it's interacting with. But the impulse is going to be either the change in momentum is equal to the mass times the change in velocity, or the net force times the change in time. If we think about egg number 1, or egg A, we know that both eggs have the same mass. They're also affected by the same acceleration because it's the acceleration due to gravity, which means that they have the same change in velocity. That's going to identify for us that the impulse of the objects is going to be the same, which means that the change in momentum is going to be the same. It also shows us that the change in velocity is going to be the same. Now let's consider the force. We know that the momentum is the same, or the change in momentum is the same for both objects. We know that when an egg hits the floor, it's much more likely to shatter than when it hits a pillow, which implies that the force associated with the egg hitting the tile is greater than the force associated with the egg hitting the pillow. That means that the net force on object A is greater than on object B. In order to make the net force times the time come out to the same change in momentum, that means that the change in time has to be less for object A than it does for object B. The last thing we want to consider is the acceleration. We know according to the second law that net force is equal to mass times acceleration. We've already determined that the net force on object A is greater, and since both objects have the same mass, that means that the acceleration on object A has to be greater as well. Last up, let's compare what the graphs would be for object A and object B in this case. If both objects were dropped at the same time, object A might have a scenario that looks like this. The force increases quite a bit, a time period passes, and then the fall is complete. So this is considered A. If we now consider object B, it's dropped at the same time and it begins to hit at the same time, but its time frame of impact is longer, which means that it creates a different shape of a curve. So this one is for object B. If we look at the area under the two curves, however, we get the same impulse, but a very different shape. This is what helps us identify that object B is much less likely to break than object A, because object A has a greater force applied over a shorter period of time, and object B has a lower force applied over a longer time. The lower force applied over a longer period of time is how car airbags and helmets help protect us during collisions. The objective here is to increase the time period of the interaction so that the force applied is reduced. Hopefully you made sense of all those great relationships and you'll be able to do it on your test.